Good morning, my name is Donald Bell. I'm from the UK, I live in London. This is my first visit to Atlanta and G4G. However, 4 years ago, one of my projects came here because Laurie Brokenshire used it as his exchange. Now, when I was a student, I used to read the Martin Gardner column in the university library every month, and I learned all about the puzzles of Sam Loyd and the geometric dissections of Harry Lindgren, and of course the polyominoes of Solomon Gollum. So today I'm going to talk to you about dissections and about polyominoes. Now it gets a little bit heavy, so what I've done is to put all of the details into a paper, which is part of the gift exchange, and there's also a little gift that I'll give you tomorrow when you collect them. And as well as that, I've created a web page, and you can download this presentation and all sorts of other things as well. So we're going to start with the famous dissection of the Greek cross into a square by Sam Loyd. What I want you to notice is the little triangle, which I shall call Sam Loyd's triangle. Its sides are 1 and 2, and of course root 5. And the question is, if you're, first of all, the Greek cross is one of the 12 pentominoes, things made from 5 squares, and the square is one of the 5 tetrominoes, things made from 4 slightly larger squares. So if there's a dissection of pentominoes into tetrominoes, there are going to be 60 of them. That is Sam Loyd's dissection and 59 more. And there's a group at the Politecnico di Torino in Italy who have actually studied all 60 of these, and they've got diagrams on their website which are absolutely beautiful. Now, one of the questions that they came up with is there some sort of universal polyomino dissection so that you could dissect all of the tetrominoes into all of the pentominoes with the same group of pieces? And this is the group of pieces that they came up with. As you can see, there are 5 of Sam Loyd's little triangles. There's a trapezium, there's a quadrilateral, and there's 2 rather peculiar shapes as well. So I got to thinking, are there any more universal polyomino dissections? And in particular, might there be one where all the 9 pieces are different, and might there even be an 8-piece one? And more to the point, how do you go about actually finding it? Well, it's fairly obvious that most of the pieces are going to be made up from squares and little Loyd triangles. But as soon as you start putting them together, you discover that you've got about 30 or 40 of them. And so the problem is, how do you scoop out a group of 8 or 9 pieces and then check them against all of the 17 polyominoes? By the way, I'm using the word polyomino to mean only tetrominoes and pentominoes. As Humpty Dumpty said in Alice in Wonderland, words are what I define them to be. Okay, so this is actually quite a hard problem. And when an engineer like me has a hard problem, what he does is to look for a much easier problem. So this is a much easier one. Here I've only got 3 target shapes, and I've only got 7 plausible pieces that might go together to make up this universal dissection. So each of my plausible pieces has got a letter, V, I, L, T, W, Y, and R. And here's what I do. First of all, I try and make the cross shape with some of the pieces. Now, there are more pieces than I need because the area of each of the target shapes is 21, and the total of all of the pieces I've got is 29. So there are going to be some pieces left out. But as you can see, there are many ways of making this cross shape, and the first one and the third one on the screen are made with the same group of pieces. So I've actually got 3 different groups of pieces that will make this shape. And to put it in mathematical terms, I've got a set of groups of pieces. Sorry about that, but it's a bit more set theory coming. So when I do the same thing with the block shape, I get another set of 3 groups. And for the gamma shape, the same thing. Now you can see that in the red lettering, the same group appears in each set. And so we've got a universal dissection of those three pieces. And here's another way of looking at it, done in a mathematical form. As you can see, each of the big circles is a set containing all of the groups that make up one particular target shape, either the block, the gamma, or the cross. And that group that we found before, VLTRW, is right in the middle. So now we get to the hard bit. How do you go up from 3 target shapes to 17 and from 7 plausible pieces to 30? Well, all of the details are in my paper. So here are the results. There are indeed a set of 9 pieces that are all different that will make all of the polyominoes. There's a set of 8 pieces, and that set is what you're going to get tomorrow. In beautiful acrylic, you and your grandchildren will have great fun putting them together to make all of the pentominoes and all of the tetrominoes. And I got an email this morning from the people who made the set that you're getting, and they've decided to market it, and that's what it will look like. Sorry, you're not getting that one. So that's what they look like, and if anybody finds a set of 8 pieces that are all different, please let me know, because some of you have got access to big computers and lots of bright PhD students. I look forward to getting an email. Thank you very much.
Thank you very much.